Section: Introduction. In this section, we explore the concept of pareidolia, which is the tendency to see patterns, like faces, in random stimuli. This phenomenon is common in humans and even observed in animals, such as rhesus macaques. We recognize that pareidolia can serve as a valuable tool for studying visual perception in both humans and machines. To investigate this, we introduce a dataset called Faces in Things, containing 5,000 images of pareidolic faces. We examine whether modern computer vision systems, specifically a neural network trained on the wider face benchmark, can detect these pareidolic faces. Our findings reveal that the network struggles with this task, even with relaxed detection criteria. By fine-tuning the model using our dataset, we establish a strong baseline for pareidolic face detection, indicating that machines can improve their performance in this area. We also consider how to enhance machine performance to match human detection capabilities without relying on pareidolic training data. Our experiments reveal that fine-tuning models to recognize animal faces significantly boosts pareidolic face detection, suggesting an evolutionary basis for our ability to identify faces in various contexts. Furthermore, we investigate why pareidolic faces are not ubiquitous and why certain textures trigger this effect more frequently. We propose two simple models that help explain the conditions under which pareidolia occurs, confirming our predictions through experiments with both human subjects and detection models. Through our open-source dataset and findings, we aim to advance the study of face pareidolia within the computer vision community. We also review related work in face detection, noting the evolution from early methods like the Viola-Jones detector to modern convolutional neural networks. We highlight the unique nature of face detection in the human brain and the mechanisms behind pareidolia, emphasizing the need for a comprehensive dataset to further explore this intriguing phenomenon. Section Summary. In this section, we introduce pareidolia as a common phenomenon where humans perceive patterns, such as faces, in random stimuli, and present our dataset, Faces in Things, which contains 5,000 pareidolic face images to investigate how modern computer vision systems detect these patterns. We demonstrate that existing face detection models struggle with pareidolic images and explore methods to improve their performance, while also proposing mathematical models to understand the conditions that induce pareidolia. Section: Faces in Things Dataset. In this section, we describe the Faces in Things dataset. To fill a gap in our research, we start by selecting candidate pareidolic images from the LAION5B dataset, which contains 5.85 billion image text pairs, with 40% of the captions in English. We use clip retrieval to gather images based on text queries like pareidolia, faces in things, and accidental faces. After downloading the images, we check for duplicates and resize them to 512 by 512 pixels while keeping the aspect ratio intact with white space padding. We manually annotate the images using the VGG image annotation tool, removing any that feature actual human or animal faces. Our annotations include bounding boxes around pareidolic faces and basic facial attributes, which could be useful for future studies. We randomly split the dataset into training, 70%, and testing, 30%, sets, referring to it as the pareidolic dataset. For our experiments, we also utilize additional datasets. We compare average faces from our pareidolic dataset with those from the wider face, human, and animal web, animal, datasets. Wider face is a well-known benchmark for face detection, containing over 32,000 images and nearly 394,000 faces, with significant variability in scale, pose, and other factors. We use the provided splits for training, validation, and testing, calling this the human dataset. The animal web dataset includes over 22,000 faces from various species, annotated with key facial landmarks. We convert these landmarks into bounding boxes by creating the tightest box around the points and expanding it by 15%. To explore whether pareidolia can result from common data augmentations, we apply Level 3 corruptions from the COCO-C and ImageNet-C datasets to the wider face images, including a Sobel filtering corruption that reduces reliance on texture information. For our models, we use retina face, which performs exceptionally well on the wider face dataset. We conduct experiments with both MobileNet and ResNet 50 backbones, ensuring consistent experimental conditions using the PyTorch_RetinaFace repository. We fine-tune pre-trained models for 10 epochs with specific parameters, confirming that this approach does not negatively impact performance on the original wider face training dataset. While fine-tuning on the Pareidolia, Animal Web, wider face, and corruption datasets, we replace images in the original training data with those from the target dataset 90% of the time to help the network learn without losing previous knowledge. We then measure the average precision, AP, of the MobileNet and ResNet 50 RetinaNet architectures on the Faces in Things dataset. The results show that while existing pre-trained models exhibit some pareidolia, they do not perform as well as models specifically fine-tuned for detecting pareidolic faces. Models trained solely on human faces show limited activity on the Faces in Things dataset. We also investigate how pareidolia might emerge. The diversity in the wider face dataset raises questions about what additional experiences models need to develop pareidolia like humans do. The Faces in Things dataset allows us to explore this by modifying the training data. We examine various training interventions, including adding data augmentations and animal faces, which could enhance the model's ability to detect pareidolic faces. Animal faces, with their greater variation, may lead to more false positives and thus a stronger sensation of pareidolia. Our findings indicate that certain corruptions, like Sobel filtering and motion blur, slightly improve pareidolic face detection, while adding animal faces significantly boosts detection capabilities. We also find that fine-tuning on pareidolic images enhances animal face detection. We visualize the model's inner representations across different datasets, showing that the representations of animal and pareidolic faces cluster together, suggesting their relative similarity compared to human faces. We emphasize that we filtered the Faces in Things dataset to exclude images of real animals. Section Summary. In this section, we describe the creation of the pareidolic dataset by sampling images from the LAION5B dataset, annotating them for pareidolic faces, and dividing them into training and testing sets. We also explore how various training interventions, including the addition of animal faces, can enhance algorithms' ability to detect pareidolia, revealing that such modifications significantly improve detection performance compared to models trained solely on human faces. Section: Modeling Pareidolia. In this section, we present two straightforward models of pareidolia, aiming to describe its high-level structure. Both models predict a peak in face detection related to the complexity of an image. We provide experimental evidence for this pareidolic peak in both humans and machines. For our Gaussian model of pareidolia, we identify two key processes: the random generation of candidate images and the face detection process that identifies pareidolic images. We represent the image generation as a sum of independent normal distributions, each contributing a zero mean Gaussian with a specific variance, multiplied by a mode image. The generated image is a weighted sum of these modes. In our face detection process, we conceptualize matching an image to a template and generalize this to distributions of template images. The target pareidolic image is represented as a vector of independent coefficients. The probability of detecting a pareidolic value at each mode follows a Gaussian distribution. We note that the variance of the random process generating pareidolia and the variance of the likelihood term are crucial for understanding how closely a mode must match the target image. To predict peak pareidolia, we analyze the optimal mode variance for detection. While we often cannot design a random process for each mode individually, we can choose between processes with different numbers of modes. The probability of detecting the target object is the product of the probabilities for each mode. Our predictions indicate that there is a peak in pareidolic detection probability for random image generation processes with a moderate number of spatial modes. Too few modes result in insufficient complexity, while too many modes make pareidolia unlikely due to the need for many modes to match the target values. Next, we introduce a higher-level feature model of pareidolia, which builds on the Gaussian model but incorporates more realistic aspects of human perception. We assume that detecting an object requires specific features to be present in designated spatial regions. Each object template has regions where certain features must be detected, while others should not. We model the existence of features as a spatial Poisson process, where the probability of detecting a certain number of features in a given area is defined. To detect a pareidolic instance, we need to find the correct features in their respective regions while ensuring that incorrect features are absent. Assuming independence and uniform detection rates, we derive the probability of detecting the object. For a simple case with 2 eyes, a nose, and a mouth, we find that the probability of pareidolic detection also exhibits a peak, governed by the complexity of the random image. If the feature detection rate is too low, we won't generate enough features, and if it's too high, the chances of finding the right features in the right places diminish. Thus, there exists an optimal rate for pareidolia detection.